Welcome everyone in lecture number 13. In this video lecture, I will tell you about inverse Laplace transform. You know about Laplace transform where you are given the function ft, right? You take the Laplace transform of ft and you get the function of p. This is a time domain function and this is a function of p, where p is a parameter which is real or complex. The inverse Laplace transform is taken of this function. हम इस function का inverse Laplace transform लेते हैं. That means we take the inverse Laplace transform ILT of fp. If we take the inverse Laplace transform of this function, then what is the answer? The answer is ft. That means you get this function. This is the original function. You get back this original function by taking the inverse Laplace transform of fp. And this inverse Laplace transform is of the function fp is always unique. It never happened that you get some other function of t that is different from this ft. You always get this function by taking the inverse Laplace transform of this function, which is the Laplace transform of ft. So in other words, you can also say that there is one-to-one and on-to correspondence between ft and fp. Okay. Now the question is how to compute the inverse Laplace transform of fp. Is there any formula to compute the inverse Laplace transform? No, there is no formula. But there are some standard methods to compute the inverse Laplace transform. So very simple method to compute the inverse Laplace transform is that if we know the Laplace transform of any function, for example, we know that the Laplace transform of 1 is 1 upon p. So if we are given the function 1 upon p, then we can directly say that its inverse Laplace transform is 1. Because we know that 1 is the 1 upon p is the Laplace transform of 1. So inverse Laplace transform of 1 upon p will be 1. Similarly, we know that Laplace transform of t raised power n is gamma n plus 1 whole divided by p n plus 1, right? Where n is greater than minus 1 and p is greater than 0. That means inverse Laplace transform of gamma n plus 1 whole divided by p n plus 1 will be equal to t raised to the power n, right? You can also write it as Laplace inverse of 1 upon p raised to the power n plus 1 is equal to Tn whole divided by gamma n plus 1. By linearity property of inverse Laplace transform, you can take constant terms outside. Okay. So this constant term can go in the denominator part of t raised to the power n. So that gives you the inverse Laplace transform of 1 upon p raised to the power n plus 1, which is a pure function of p. Okay. Similarly, we have Laplace transform of t raised to the power n in terms of factorial also. That formula is for n greater than minus 1. N is not a positive integer here. But if n is a positive integer, then you can write this as, here you can write in place of gamma n plus 1, you can write n factorial. Okay. So you can directly write uh, let me write the formula first of all. Laplace transform of t raised to the power n is n factorial divided by p raised to the power n plus 1 if n is a positive integer. If n is a positive integer, in that case, gamma n plus 1 can be written as n factorial. So from this formula, we can conclude that Laplace inverse of 1 upon p n plus 1, we take the Laplace inverse of this part and take n factorial outside and take this n factorial in the denominator of t raised to the power n. So this is equal to t raised to the power n divided by n factorial when n is a positive integer. Next is Laplace transform of e raised to the power at. You know that Laplace transform of this function is 1 upon p minus a, where p is greater than a. So you can quickly conclude that Laplace inverse of 1 upon p minus a will be e raised to the power at. If there is negative sign, then there is positive sign, and for positive we have negative a here. Okay, so take care of this. Similarly, Laplace transform of sine hyperbolic at is a upon p square minus a square. P is greater than mod a. This implies Laplace inverse of a upon p square minus a square will be equal to sine hyperbolic at. To remove this constant term, we take this constant part in the denominator of sine hyperbolic at. So we can write, let me draw a separating line here. Okay, so this implies Laplace inverse of 1 upon p square minus a square is equal to sine hyperbolic at whole divided by a. Next is Laplace transform of cos hyperbolic at is p upon p square minus a square. This implies Laplace inverse of p upon p square minus a square will be cos hyperbolic at. Okay. Laplace transform of sine at is a upon p square plus a square. This implies Laplace inverse of 1 upon p square plus a square will be equal to sine at divided by a. Laplace transform of cos at is p upon p square plus a square. This implies Laplace inverse of p upon p square plus a square is equal to cos of at. So these are some standard formulas that are derived from the formulas of Laplace transform directly. You can use them directly in the questions. Okay. There is also linearity property held by inverse Laplace transform as by Laplace transform. Linearity property of inverse Laplace transform. This property says that if we are given the expression like C1 F1p plus C2 F2p is the linear combination of two functions, then its inverse Laplace transform will be equal to C1 Laplace inverse of F1p plus C2 Laplace inverse of F2p. This is the linearity property held by Laplace inverse. So let me take some examples which are very simple. For example, find Laplace inverse of 1 upon p raised to the power 5. Okay, so uh, how to compute its Laplace inverse? I have told you the formula. Laplace inverse of 1 upon p raised to the power n plus 1 is equal to t raised to the power n upon n factorial if n is a positive integer. So its Laplace inverse will be equal to, first of all, we'll write the formula. Laplace inverse of 1 upon p raised to the power n plus 1 is equal to t raised to the power n whole divided by n factorial, where n is positive integer. This implies Laplace inverse of 1 upon p raised to the power 5 will be equal to, so if you convert this in n plus 1 form, n will be 4. So this is equal to t raised to the power 4 divided by 4 factorial. This is the answer. Directly by using the formula. No need to do anything. Example number 2. Find the Laplace inverse of 1 upon p raised to the power half. Here n is not a positive integer. N is a number greater than minus 1. So we use the formula, this one, in terms of gamma. Okay. So Laplace inverse, let me draw a straight line here. So Laplace inverse of 1 upon p raised to the power n plus 1 is defined as t raised to the power n upon gamma n plus 1 for n is greater than minus 1. N is not a positive integer here. So Laplace inverse of 1 upon p raised to the power half. इसको हम n plus 1 की फॉर्म में अगर लिखेंगे तो क्या लिखेंगे? हाफ को आप ऐसे ऐसे लिख सकते हो, Laplace inverse of 1 upon p raised to the power वन अपॉन टू माइनस वन प्लस वन, ऐसे लिख सकते हैं. ओके, सो हियर n इज 1 अपॉन टू माइनस वन, एक तरह से माइनस हाफ. n is equal to minus half here. So Laplace inverse of 1 upon p raised to the power half is equal to t raised to the power minus half whole divided by gamma minus half plus 1, that is equal to t raised to the power minus half gamma half, and gamma half is under root pi, so this is 1 upon square root of t into pi. Next example is example number 3. Just find the Laplace inverse of 1 upon 2p minus 5. अब ऐसा तो कोई फॉर्मूला नहीं है आपके पास 2p माइनस 5. आपके पास जो फॉर्मूलेज हैं उसमें लाप्लास इनवर्स ऑफ p माइनस समथिंग है, p माइनस समथिंग. तो आपको इसे p माइनस की फॉर्म में लिखना पड़ेगा पहले. तो आप इसे कैसे लिखोगे? आप इसे लिखोगे दिस इज इक्वल टू Laplace inverse of 1 upon p minus 5 by 2. 1 upon 2 will be taken as common. Okay. So here this is now in the form of 1 upon p minus a. So we know that Laplace inverse of 1 upon p minus a is e raised to the power at. So Laplace inverse of 1 upon p minus 5 by 2 is e raised to the power 5 by 2 t. So Laplace inverse of 1 upon 2p minus 5 is equal to 1 upon 2 e raised to the power 5 upon 2 t. Example number 4 is find the Laplace inverse of p upon p square minus plus 16. So this is of the form p upon p square plus 16 is of the form Laplace inverse of p upon p square plus 4 square. इस टाइप का फॉर्मूला है हमारे पास. ये p square plus a square, this one, its Laplace inverse is cos 18. So you have to memorize all the formulas. Cos 4t. Okay. Next, find Laplace inverse of 2p minus 5 whole divided by p square minus 9. So we solve it. First of all, we separate these two terms. This is equal to Laplace inverse of 2p upon p square minus 9 minus Laplace inverse of 5 upon p square minus 9. Now we take this 2 outside the bracket. p upon p square minus 9, and we take this 5 also outside the bracket. 1 upon p square minus 9. Now this is its Laplace inverse is cos hyperbolic 3t, and here we need 3 because here we have 9. So Laplace inverse of a upon p square minus a square is sine hyperbolic at. So we multiply and divide by 3 so that we get 3 here, and it is its Laplace inverse will be sine hyperbolic 3t. Next example is find the Laplace inverse of 3p minus 16 whole divided by p square minus 16. Do it in the same way as I have done this example. The answer is, let me write the answer. Answer is 3 cos hyperbolic 40 minus 4 sine hyperbolic 40. You do it by your own and tell me whether your answer is verified or not. Okay. I hope you understand the lecture of finding the inverse Laplace transform. These are the elementary methods of finding the inverse Laplace transform of any function of p. Some more advanced methods we'll see in the next video lecture. Thank you so much for watching the video.